All right, let's go ahead and get started. Any questions about anything we've done? Or anything about the class before you get going? You should have grades in Canvas for your first web work. Let me know if they don't look right to you, but they should. Everything should be accurate right now. When does the written homework due? 30th, which is Wednesday. Okay. So that's over section 5.5 and 6.1. So you should be, I believe that we completed both of those. If I haven't already said this, I think it'll be rare that you'll be able to complete, any given written homework without coming to me for help. Same with the online homework. Some of them are tricky. So they're all things you can do, but maybe not everything that's on there. Maybe not everything on there is something you can do without reaching out to a resource, classmate, me, Stack Exchange. Go ahead.
For the written homework, do you have to print out the worksheet or
No, you
can do it on a separate paper?
Yeah, you don't have to print that out. So I think I put that on there, but yeah, I am purposely not giving you no space to get your stuff done on it. But yeah, you don't have to print it out. Just do it on a separate paper or an iPad or whatever. Whatever is easy for you to get a photo or a PDF back to Canvas and when you're ready to submit it. Good question. What else? All right, so we're going to finish up integration by parts. There's a couple things I wanted to show you. We did this e to the x sine of x last time. So let's do a definite integral. So I want to integrate from 0 to 1 arctangent of x. How do we get started? We need a reminder of how integration by parts works. So we can start by defining u, right? So if we start by defining u, what's the fallout from that? What other things kind of get defined for us? dv. So let's make a choice. What are u and dv? More importantly, how do we make these decisions? What kind of guiding lights are you thinking about? So in the past, what did we choose for u on this one here?
X squared.
Do you remember why we chose that?
They made it simpler.
So differentiating it made it simpler, right? So that's one thing we look for. One thing I didn't really focus on, but think of the other side of that coin. Think about what's going to get simpler, or think about what's simply not going to get more complex. So if we differentiate x squared, what do we have to do to e to the x in this example? Integrate it. What happens when you integrate it? It stays the same, so it doesn't get more complex. So this thing here, so what are the parts we can split this up into?
Arctan x and dx.
That's about, we cannot split up the arctangent from the x. Arctangent is like an operator, it has to operate on something. It's kind of like sine of x. Can't really separate the sine from the x and without really just destroying what that function does.
If it was x squared, you would have to do use substitution first and then integration by parts?
I think that's probably accurate. Okay. Let me ask you this: if it was arctangent of x squared, what tells you that substitution is something you'd like to do? It's you have a function composed with another. So that's one thing that I know. Like I said last time, choosing between by parts and by substitution is sometimes tricky, but those are the kind of things to think about. It's good that you're seeing that distinction. So all we really have is the arctangent x and dx. So basically, those are the two building blocks we have to choose where they go. So what do we think about where they should go?
I think arctan x should be u.
Why should arctangent x be u?
Because I don't know how to do the integral of arctan.
And that's sometimes your hands are tied for you because we don't know how to do that other one. So think about this as an analog to the natural log of x. If I can integrate it directly, I wouldn't need to use this. So you can't take an integral of arctangent x, do you know its derivative? I'm guessing it's
1/1 + x².
yeah, so I'm not gonna develop why, but yes, that is true. Does that look familiar? Okay. I'm not organized well. So if dv is equal to dx, then what's v?
X.
V is equal to x. All right. So now I think we have all the pieces we need. We fill this into integration by parts. What's that going to look like? Arctangent x. Right? For now, I'm going to leave the limits off. Going to evaluate that at the end. How are we feeling about where we are? Okay, so now remember the goal of, or kind of the game you play with integration by parts is I'm trying to trade in an integral I can't do for one that I can. Have we done that? Not as easy, but can I do the integral of x over 1 + x squared?
Yeah.
I see some head nods. How can we attack that?
U1 + x².
So now we're going to go to substitution. What tells you that you want to use substitution there? Okay, so I have u equals 1 + x squared. What does that make du? 2x dx. Will those two things alone help me do integration by substitution on that integral?
You divide the du by 2.
What's that? Yeah, divide du by 2. Good. So if I isolate x dx, what does this imply? Du over 2 is equal to x dx, which means this integral becomes what? 1/2 times 1 over u du. Okay, is that an integral we know how to do? All right. What does that become? What was that one more time? Natural log, so 1/2 natural log of u, right? So forgive my kind of roundabout organization here, but this becomes 1/2 times the natural log of absolute value of u. So now let's come to the bottom here. Now we can handle this whole thing at once, I believe. So I have the integral of arctangent x equals x arctangent x minus 1/2 times the natural log of, what was our u? Absolute value of 1 + x squared. Is that everything?
Yeah, can you explain how you went from, like, how you did, so you did use substitution.
Yep.
Right there, 1 + x², and then,
So you want me to pick up from here?
yeah,
Okay, so once we choose u for u substitution, there's a consequence that falls from that immediately, which is what? Which is what du is. So these two things, u and du, are related by differentiation. So if u is equal to 1 + x squared, du is equal to the derivative of that times dx. So once we choose u, du is essentially chosen for us.
okay,
So one thing to remind you about integration by substitution, yes, looking for those composite functions is a good place to start. But you also need, whatever your u is, you need some multiple of the derivative of this u to be present elsewhere. So the fact that we had two x dx here, or Melissa modified it to become with x dx.
You left it to be extra, so you can that's another.
Right, so this basically, that I suspect that's why Melissa did this, because this x dx here, I can just drop 1/2 du into that part of the function. Go ahead.
On the political one, very similar, like 5 over X, when you start with substitution of X.
I think I would start by parts, but I'm actually wondering if it matters. Okay. Yeah, let's talk about it. I suspect it's arctangent 5 over x, and there's something multiplied by that. Otherwise, we'll see how it works. But we can talk about that. I just don't know the specific problem. All right. Any more questions about where we are currently? Okay, what do I do with it now? Yeah, evaluated at 1 and 0. So let's drop these back in from 0 to 1. What happens when I evaluate this from 1 to 0? We get 1 times the arctangent of 1, which is what? What does that mean, first of all, the arctangent of something? Yeah, what angle has a tangent value of 1? What angle does have a tangent value of 1?
2 over 2.
I think you went one step beyond pi over 4.
Oh,
Yeah, like you found the angle and then you took a sine or cosine of it. But yeah, the angle is that 45-degree pi over 4. So 1 times the arctangent of 1, I'll just write this out in a couple of steps, minus 1/2 times the natural log of 2, minus all the stuff that happens when you put in 0. 0 times the arctangent of 0, minus 1/2 times the natural log of 1. So arctangent of 1 we said was pi over 4, right? Minus 1/2 the natural log of 2. What is 1/2 the natural log of 1? So the natural log of 1 is, or any log of 1 is 0, so I believe we are done now. How are we feeling? Ask me all the questions. Must be mastered this. All right, last one. Average value. Is this something we remember from our Calc 1 days? Okay. How do you find the average value of a function over some interval?
take the interval and you divide it by the length of the interval.
Right. So basically, I mean, how would you find the average height of the people in this room?
Not everybody divided by.
Right. So it's pretty easy when you have like a finite number of things. When you have a function over some continuous interval, you have to, how do you average an infinite number of things? The only way to do that is by integration and dividing over the width of that interval. So having said that, we know we need to integrate. What is a good place to start here?
Finding u and dv.
Finding u and dv. So let's do that. U equals something, dv equals something. What's a good choice for you?
X
How come?
returning a 1.
It becomes one, we differentiate it, so it becomes simpler. We like that. Once we've chosen that, we're saying that secant squared of x dx has to be dv, which is only helpful if we know what the integral of secant squared x is. It is tangent x. So I suspect that many of you are like beyond sine and cosine, the trig derivatives are probably a little fuzzy. Getting familiar with them again is going to be pretty crucial for some of the, especially when we get more trig in the next few minutes here. Yeah, v should equal to tangent x. All right, I think we've got all the parts. So now what does this integral become? Is the integral of tangent x. All right, is tangent of x something we know how to integrate?
Yeah.
Yes, I think we've done something like it, if not exactly. But how do we handle integrals of the integral of tangent x? Yeah, I think it's probably going to help us if we re-express this as minus the integral of sine of x over cosine of x dx. How did that help us?
Is, you know, can read it once again.
I actually don't know if I don't know if integration by parts would work, but I think there is an easier way. Go ahead. Okay, you'd like to do substitution? So what's our u going to be?
Sine x dx.
Very close. Minus sine of x, minus sine x dx. So if we set up substitution that way, is that helpful for us? So if we do the integral that way, let's just remind ourselves when we do integration by substitution. Well, let's just try it. So u is equal to cosine x, right? So I have something over u. Does the rest of that integral or the rest of that integrand get transformed using our u and our du?
Plus 1 over u du. And then the natural log of u. And just the x tan x.
Yeah, okay, let me stop you there. Let's just do one step at a time. But yeah, I believe that integral becomes negative du over u, right? And since we're already subtracting it, we might as well cancel out the negative signs. But yeah, I think integration by substitution is a good thing to do there. Du over u is much simpler, much more negative. What is the integral of du over u? Natural log of almost. Natural log of the absolute value. So natural log of the absolute value of. Yeah, do you mind if I skip that step? So I believe that is the antiderivative of x secant squared x. Any questions on how we got there so far?
Do we need to add the numbers?
Yeah, so we're not done.
Oh.
I'm just taking a pause to make sure that we understand. I think that 95% of this job is getting that. Plugging in the limits is simpler. What's up?
I'm a little confused on when you did the u substitution.
Yeah.
So that around there.
So right here.
Yeah.
Okay, are you good with why we chose u equals cosine x? Okay. And why du is this?
Yeah.
Okay. So using like this translation, denominator simply becomes u. The numerator or sine x dx is not exactly what we said for du, which is why we had to, maybe I should have put negatives back in. But this, the way I originally wrote it was this. We were subtracting this, so I had a negative du there. But then from there, if we integrate it from there, we're gonna get negative natural log of the absolute value of cosine x. Either way, you're gonna cancel out the negative sign that's on the outside of the integral. You okay with that?
Yeah.
Okay. And then what's the integral of du over u? One more time. Natural log of the absolute value of whatever that denominator is. Okay, so we got our antiderivative. Now what do we do with it?
Evaluated.
Okay, so pi over 4 times the tangent of pi over 4 plus the natural log of the absolute value of cosine of pi over 4 minus whatever happens when you plug in 0. 0 tangent 0 is 0 plus natural log of cosine of 0. What's the tangent of pi over 4? 1. We just asked this in the opposite direction. Plus the natural log of whatever the cosine of pi over 4 is. Root 2 over 2. Is that it? Yeah, everything else goes to 0, right? What's the cosine of 0? 1, natural log of 1 is 0. So that is the value of that definite integral. Are we done?
No.
No, what has to happen then?
The average divided
Right, so we have to divide that by the length of the interval. So I'll say average value equals pi over 4 plus natural log of radical 2 over 2 all over pi over 4, right? Will anybody be offended if I don't simplify beyond that? Question? -1. Where? From this bracket?
Yeah.
I don't think so.
It's kind of 0 as well.
It is, but then you take the natural log of 1,
Oh, yeah.
which is 0. So I believe this all.
Oh, yeah.
Falls on.
0.
Do you agree with that?
Yeah.
Okay. Melissa?
When you're integrating tan of x, is the tan of x you're integrating negative?
It shouldn't be.
Because the thing is, when I integrated it, since the du is negative sinus, when you take the negative out and then like subtract the integral from the.
So we did, I don't think we dealt with the negative sign in exactly the way you're saying, but I think we did deal with it correctly. So we started with x tangent x minus the integral of tangent x. Re-expressed it as sine over cosine. And then when we did the substitution, our du ended up being the opposite of this, being the negative version of this, right?
Yeah.
So I believe that's why these negative signs essentially cancel out.
Okay. I originally had a x at one.
Unfortunately, the thing that plagued you when you were in junior high with negative signs literally goes away. Every once in a while, I still have one too many or one too few, but yeah, it's just hard to keep track of. How are we doing on this one? All right, that's all I got for you for integration by parts. So let's get a little more heavily involved with the trig integrals. So in your math careers, you've seen a ton of trig identities. Let's hear some of them. We've used a couple of them today. Okay, so we got the Pythagorean identity, right? Sine squared of x plus cosine squared of x equals 1. And then from that, you probably have a few different flavors of this thing you recognize, right? Give me one of those.
One plus two tangent equals cosecant squared.
1 plus cotangent squared of x equals cosecant squared.
Yeah, and then you can also do tangent squared plus one equal secant squared.
Okay. And then all of these you can isolate for a single term. But you know, sine squared plus cosine squared x plus one, that Pythagorean identity. I think you can get those other two below it by dividing everything sine squared, and then starting over and dividing everything by cosine squared. So really 3 different manifestations of the same idea. Or there are other trig identities you've dealt with. Even if you don't remember their exact formulas, do you remember things you've talked about?
Like double angle form.
Double angle identities and half angle stuff. So we're going to take advantage of the fact that we can rewrite these functions in terms of other things to help us out with doing the calculus involved with them. But one other big one I want to write down is, this might be so fundamental to you, we don't even think about it anymore, but just a few minutes ago, we used this one without any real problem. Just something we know we can use. I don't expect that anybody remembers like the sum and difference identities or any of those strange ones, but we are going to use them. I will not make you memorize them for a test. I'll put that out of your mind right now. But we will have to use them and kind of know when to use certain ones. So I want to find the integral of cosine cubed. There's no Pythagorean identity that involves cubing things, right? So I can't jump straight to that. Can't really do a substitution because let's say I want to make u equal to cosine x. There is no sine of x elsewhere for me to help out there.
Question, isn't there a power reducing formula?
There is. We're going to do something that I think that formula comes from. But I don't know off the top of my head what that formula is. But one thing we rely on the fact is that even though this is not cosine squared, we do have 2 powers of cosine, right? We have at least 2 powers of cosine. So because of that, would you agree that this integral is the same as the one above it? Okay. So I can't use integration by substitution yet, but I would like to get to a place where I could. So based on our Pythagorean identities, what is something I can swap in for that cosine squared? 1 minus sine squared of x dx. First of all, do we believe that everything that we've written down is legal and true? Is this an integral we can do with the weapons we already have? How? Will integration by parts work? We just talked about that. I mean, it might. So I think we have 2 things that are clearly multiplied by each other: the cosine x and 1 minus sine squared of x. I don't know how to integrate 1 minus sine squared x, but I could probably take a derivative. Don't know what the integral of cosine x is? Sure, that's something we can do. I'm actually not sure that'll get us to the end. But one thing I do want to point out is, so basically the 2 big techniques we've talked about so far are substitution and integration by parts. Integration by parts, you know, this kind of looks like a product rule type of thing, so it looks like it might work. Something else to think about is integration by substitution. Can we split this function up in such a way so that we have some function u and its derivative elsewhere? So I'll tell right now, I'm going to lean into integration by substitution for this one. Do we see anything here that's like a derivative of something else? Go ahead.
You could possibly take the derivative of 1 minus sine squared x.
Okay, so let's try that. U is equal to 1 minus sine squared x. If we do that, then what is du? I think it'd be chain rule -2 times the sine of x times the cosine of x. So that extra sine of x is what I think hurts us because we have the cosine x dx present. So maybe that's a little bit too complex. Anybody else have anything else we can try? What if we stick with sine of x? If u is equal to sine of x, then what does du have to be? Cosine x dx, right? Does this substitution help us?
Yeah.
So if we use that u substitution, what does this integral become?
Minus
1 minus u squared du. So really, and hopefully it becomes more clear as we do more examples, but the thing we're going to be leaning into here is, can we rewrite these trig functions so that basically we have the product of some variable function and the derivative of that intermediate function we made. If they're starting with cosine cubed of x, there's no way to get that done while the function is represented that way. So we took advantage of the fact that Pythagorean identities allow us to rewrite sines and cosines and higher powers of them in lots of different ways. Question?
Integration by parts of like cosine x times cosine squared x.
I think that would work. I don't think it'd be as effective as this.
This
But-
is wrong.
Yeah, I'm actually not sure. I kind of want to try it, not right now, but I kind of want to try it, but I'm not sure it would work. I am sure we're almost done from here. So this is kind of a strange thing. It's the first time you're seeing it. Do you have any questions about kind of how we did this? Or do you not even know what questions to ask me yet? Go ahead.
When you integrate 1 minus u squared, would you put the 1 as a u or would you put it as x?
What variable are we integrating with respect to?
I guess u.
So that becomes u. So let's go ahead and integrate. What's the integral of 1? U minus
Cubed over 3.
u minus u cubed over 3 plus c, and finally cosine of x minus cosine. Yes, thank you. Sine of x minus sine cubed of x over 3 plus c. How are we doing? So in this one, I think the most difficult part, not the part that took the most time or the most work, but the most important part is knowing what your manipulation, like what identity you're going to use and what manipulation you're going to make from it. I was definitely writing a lot more on the slides for integration by parts. So there's more, I think, kind of like planning work that goes into this. But once you do that, the integral hopefully should become manageable quickly. See another one. Sine to the 5th of x times cosine squared of x. So we're going to do some rewrites. What are those rewrites going to be based on, we think? All we're dealing with is sines and cosines, and we're dealing with higher orders and higher powers. So those are things that kind of suggest that we should at least consider, or at least try, some kind of Pythagorean identity. Even there, we have a couple of choices, right? I have cosine squared and I have sine to the fifth. I would like to use a Pythagorean identity to start doing some transformations, but wait.
If we split it once to be sine cubed times sine squared to get the first one, would we also have to split again the sine cubed that came from the sine to the.
Okay, so I got, certainly this is true, right? We can break up the fifth power sine into this, right? Do we see a way forward with substitution after that? Go ahead.
Swap out sine squared x with 1 minus cosine squared.
Let's try that. So now we have sine cubed of x times 1 minus cosine squared of x times cosine squared of x dx. One thing I want to take us back to is here. We used u of simply sine of x, right? Not any power, not any higher power, just sine of x, which means du was cosine x dx. And I didn't keep it written down here, but I think the first thing we tried was sine squared, right? Or 1 minus sine squared. What was the problem with that? Why didn't that take us to where we wanted to go?
They didn't cancel out the cosine.
Right. So I mean, all we had left to kind of to handle was that cosine, and making u sine squared of x gave us basically more complicated derivative. So is there a substitution we can do at this point? Or not quite yet? I'm going to go ahead and split the I'm going to take another pair of sine powers out of here. So I'll do sine of x times 1 minus cosine squared of x squared times cosine squared of x dx. So we started with higher powers than one of both these trig functions. Now I have sine of simply x, just sine of x, a linear sine, right?
Can we do substitution with playing 1 minus cosine squared x?
Let's try it. If we do u equals 1 minus cosine squared x?
Yeah.
Okay. U equals 1 minus cosine squared of x, then what does du become? -2 cosine x sine of x becomes positive, right? So chain rule. The derivative of negative cosine squared x becomes -2 cosine x. That's the outside function. Derivative of cosine is negative sine, so I believe the negative signs will cancel. Okay, so I believe that's a good u and du. Can we transform our integral using those things? What's the problem? Why can't we do it?
Yeah, the extra cosine. Yeah, we can't get rid of it.
Yeah, I think we have that extra cosine squared on the right side of the integral. So yeah, substitution is good. Here's the thing that makes these things, I think, deceptive is the fact that now our substitutions are probably going to be simpler. Did you ever hand up or you just?
Yeah, I think you should just keep cosine.
Let's try u equals cosine x. If u is equal to cosine x, what does du become? Negative sine x dx. What does that do for this integral? So let's start putting things in. Can we also say that negative du is equal to sine of x? So now this integral becomes the integral of negative du times 1 minus u squared times u squared. That looks weird to write it that way, but I think it's true. We okay with that? Is that an integral we can actually do? I don't want to do it the way it's written, but I think we can do it. So what's 1 minus squared? 1 minus 2u squared plus u to the 4th times u squared. I don't want to do that either. Yep. So u squared minus 2u to the 4th plus u to the 6th du. So again, the really difficult things to kind of determine here and to kind of train yourselves to do are, what are the manipulations I have to make? What's the substitution that I'm going to kind of rely on? Let's finish this integral, and then I got some kind of guiding questions that help me think about kind of this process. Can we do this integral that I have written now, the one at the bottom of the screen? Yeah. Tell me what it is.
Negative. U to the 3rd over 3.
Yeah.
Minus 2u to the 5th over 5. U is 11.
And what should I drop in now? What should I do to finish?
What?
Right, so negative cosine cubed x over 3 plus 2 cosine to the 5th x over 5 minus cosine to the 7th x over 7. Oh, it's terrible. Plus c. One thing we didn't do that I think we should at least think about what would happen if we did. We started. I mean, I don't think anybody even suggested dealing with that cosine squared, right? Or transform. So we started translating sines into cosines, but let's at least think about what would happen if we translated the cosine into sines. So we only have a squared there. So what does that become?
1 minus sine squared x.
So the integral of sine to the 5th of x times 1 minus sine squared of x. So let's think of it this way. The substitution we actually ended up doing that helped us was cosine of x, right? So let's do the opposite here. Let's do sine of x. If u is equal to sine of x, what happens from there? du is equal to cosine x dx, right? Would that help us integrate the new thing that we have there? No, we don't have any cosines to work with. The reason I point that out is because that should kind of give us a guideline as to, we have sine and cosine both to higher powers than 1. Which one should we start manipulating? So can we generalize this a little bit? Why was sine the correct one to start manipulating, transforming sine squareds into cosine squareds? Why did this substitution work? The u equals cosine x from this step. Why did this work when I believe this one would have failed?
Because, for the DU, you plug it in for the other one.
Right.
You end up with just U.
So for this one, we really needed this last sign here, right? So what does that tell you about, what about the powers of these trig functions up here? The higher the power, the one we should go for. With the higher power. So we think we should transform the higher power. Well, yes, we went for sine. Initially, we went for sine. Did we go for it? Did it work because that was the greater power?
Or did it work because it was odd?
Or did it work because it was odd? Why does that matter?
Because then you cancel it.
Right, then you have the one that you can remain, right? I have no chance here of getting a single cosine.
So on this, on the other one, the DU would have left us over with this, with the trig function, and we wouldn't fit it.
Right, then you can't, that substitution won't take you. It won't get you to a place where you can actually integrate because you'll have two variables.
Yeah.
So. One thing to look for is the fact that we can have that single power. To kind of help us to become that DU for us is really important. So keeping that in mind. Actually. Yeah, we can do this. So. Now all I have is an even thing. Right? There is no odd cosine or sine to do this with. So there's other identities we have to rely on. Probably haven't seen them in a while, but we're going to look at a double angle identity. Does anyone happen to remember what those things look like? You do? That's one of them. Sine of 2x equal to 2 sine x cosine x. That is true, but I don't think that one's going to get in here. We have a square, we don't have a double angle. How about the double cosine identities? I'll remind you. Cosine squared of x minus sine squared of x. And you might remember, by the way, I do not expect you to remember these things. I remembered it because I was doing this. But I do expect you to know how to Google or look at your textbooks and figure out where they are. Because a lot of these is just getting familiar enough with the identities to know that, oh, that's the one that's going to help me.
Would this be provided like a formula sheet on a test?
I mean, yeah, I can't promise you to give you the Pythagorean identities because those are pretty fundamental to, just how plane geometry works. But I doubt you've ever had the double angle identity proven for you. They're kind of just given to you, so I don't expect you to have them memorized. Go ahead.
And then there's like 1 plus 2 cosine squared x.
It should be 1 minus, right? So the Pythagorean identity allows us to rewrite either one of these, right? I'm actually going to rewrite I'll do 1 minus sine squared x minus sine squared x. Why would I have done that?
Because you just replace cosine squared x.
Right, so I'm doing the Pythagorean identity. So that's why it's true. Is it clear yet why I am doing this? So we don't have time. So let's at least talk about what we would do and then we'll finish it up on Monday. So that double angle identity, cosine of 2x is equal to cosine squared x minus sine squared of x, which is also equal to 1 minus 2 sine squared of x, which is also equal to 2 cosine squared x minus 1. Look at the function I'm trying to integrate. Is there anything that I can make use of here? Go ahead.
You want to substitute the sine squared x with cosine 2x minus 1 over 2.
Right, so how did you get there? Right, so this last one, let's go ahead and isolate things. So cosine 2x minus 1 equals negative 2 sine squared x, which implies that sine squared x is equal to 1/2 minus 1/2 cosine 2x. We can't integrate sine squared of x, right? But can we integrate this other thing that we just found out that it was equal to? Yes. I have 9:55, so let's not do that right now. We'll finish that on Monday. As always, I'll stick around if you have any questions. Otherwise, have a good weekend.